ask you a couple of quick questions? Hopefully they're quick. So I'm trying to finish up this lab, and I'm struggling to figure out this math.
Yes.
It's the same math that I've been struggling with all of the quizzes too. I just
So this
can't
one,
get it.
let's see, where's the handy? Yeah, so then you can use this. It's
Okay.
like X to solve for X. So for number 2, so if X is log of T2 over T1 over log, and then the tricky part is flip them. And then so it
Okay.
tells you, so you look at 1 and 2. So we're trying to find the order for B, so solving for X for B.
Right.
So then you can take, so your T2 can be 20 then, so we'll do this as 2. So then you'll do log of 20 over, so convert that to seconds, so 61
Okay.
over log of, so we're just looking at B because that's the only one that changes.
Okay.
So log
So
of
then it would be
C1, like that.
10 over 20.
Yeah,
Okay.
and that should give you about 1 or so. At least that's what other
Okay.
people have been getting.
Okay. Thank you.
So, I don't remember this, how to calculate the molar mass movement and the molarity from just the percentage.
So you have to set it up. So if it's a 0.6%, that's usually weight per volume. So the first thing I would do is assume 100 milliliters. So we have 100 milliliters, 0.6 grams of our urea. And it would ask for molarity. We just need to convert this to moles. So divide 0.6, divide by the molecular weight, divide by 0.1 to give you your molarity.
And then one other quick question. I just wanted to make sure that I did this right.
This looks odd. Yeah, so I would set this up like that. So something went wonky there.
Okay.
But then this looks fine though, the M1V1 stuff.
Okay.
Yes, that looks funny.
Okay. Thank you.
Yeah. Is that a blood orange or? Yeah. in the Thursday labs.
Oh, I see.
Could we be in the Thursday lab?
You could be in the Thursday lab.
Just everybody's.
I do have Tuesday lab, people that have to do the equilibrium lab, so. It shouldn't be too hard. I'm not
Is there
anticipating.
lots of math on it?
Like minimal math,
The math I haven't done yet.
probably the line Buck-Weaver plot.
No. I'm worried about So the Tuesday people have to do the equilibrium lab today.
So we have lab and then, so we have our normal lab today, but also the practical.
And check out, yeah, because we have to check out this week. I guess we could push it back, but I don't want to. Because then we're just meeting to like check out and take a brief.
Is there
Lab
final
final.
extra credit on it? Lots of.
No, but we're just gonna weight it like the same as a lab, so
Oh, okay.
it won't be too crazy. All right, so let's go ahead and talk about the end of the year, since it is here. All right, so we are here at the end of the quarter, week 10. Can you believe it? I can tell you guys don't believe it. I'm still missing a ton of work from a lot of people. I'm looking at everybody. Everybody's missing a ton of work. All right, so here's the plan. So today, right, we have to do for the Tuesday lab people, for since of our snow day, we have to do our equilibrium lab. And so if you look in the syllabus, I promised a lab final, and instead I just kind of made it a shorter version. There's still going to be some math. There's going to be like a little bit about Le Chatelet's principle too, like interpreting the line Buck-Weaver plot, stuff like that. I don't anticipate it being too hard, especially because it's open note, open all your labs. So use that to help you. So today we'll do lab final. I'll just kind of call that lab final in quotes. So it's just going to be weighted the same as a lab, since it is short. So there's no physical manipulations. It's just kind of taking a little mini quiz. And I think it's only 7 questions. 2 of those are like, what were your favorite labs and what was your least favorite? So try not to put too much pressure. And so that means the Thursday lab people, you'll do just your lab final and check out. So Tuesday, we're also checking out. Trying to get things. So today, I know we have a busy schedule for Tuesday, people, and I apologize for the snow day for kind of compressing stuff. So we'll do our lab final and check out today. For Tuesday, people, Thursday, we'll do the lab final and check out. That should be pretty brief for the Thursday people. And then, so my plan, so week 11, we'll do review. So review on Tuesday. So we'll do a review during class, how I usually do, where I go over, sample problems basically from the test. And then we'll do our test Thursday.
And if you can't test on Thursday, please make arrangements with me. I already have somebody emailed arrangements, so they're going to take it prior, so you should do the same if you're not going to be there, going out of town, traveling, whatever. And then my other thought was, since so many people owe me work, I was thinking maybe on week 11, especially on like the Tuesday lab time, maybe we could do like a group study session. And I will obviously be present. Like, I seriously want to like tape everybody down to the seats and like, you're not leaving until, I can't actually do that.
Will you do that to me, please?
I mean, only if you consent, I guess, to being held hostage. But yeah, that's kind of my thought, is like if we could just get everything done, just turn it in. Don't forget your papers also due, or your mini paper. So that, it's just a rough draft, so I'm not expecting anything perfect. What I just want is, at least try to get to 3 pages. And I just want to see, ideas are forming, have your, also, your journals. So I think I said to do at least 2 sources. But yeah, I try not to stress too much about it, because I know it's just a working draft, but I just want to at least see that there's content you're trying. And then this will give me time to edit it, and then you can, of course, refine it for the final paper spring term.
What's the due date on it?
I think it's supposed to be this week on Friday, but, so yeah, so it's supposed to be due the 14th. I would highly encourage that, especially for my own sanity as well, since those take longer to grade. All right, yeah.
Is that just the check-in, or is that another thing?
No, this is another thing. So the check-in could have been anything, like some people just gave me outlines or papers, but this should be like an actual rough draft of whatever your paper is. So I'm expecting 3 pages, 12-point font, double space is fine. I just want to see, some working living draft. It doesn't have to be perfect. That's why I want to edit it and offer corrections for spring.
Format is MLA.
I think JAX, which is going to be ACS, is the format. And I can post a link to it if I remember for announcements. But you can also just Google ACS format, and that's what the chemistry journal articles use. All right, other questions? And then if we need lab makeups, I would try to get those done this week on that Thursday lab. So if you need to make up a lab, email me so we can get that arranged with the stockroom. All right. Any other questions, comments, concerns as we barrel towards the end of the quarter? All right, so let's finish up chapter 19 then. And now I kind of scrambled my notes. All right, so we had left off, we're kind of talking about Q and also doing the math here. And so now we're trying to do finding equilibrium concentrations when the given equilibrium constant and initial concentrations are pressures. And so step 1 is to, of course, decide in which direction the reaction will proceed. And so that just depends on the problem, right? Maybe they give you all starting material, maybe they give you all products, or maybe you don't know, so you might have to actually solve for Q and compare it to K. And so that might be the first step, so that all depends. So it's easier, right, if you're just given all reactants, it's going to go to the right. If you're given all products, it's probably going to go backwards to the left. But then if you're given a mix and you don't know, then you have to solve for Q first. So then we know which way it's going to go. And so that leads us to step 2, where we had started kind of just defining the changes of all materials in terms of X. So we saw that previously. And so that coefficient also gives us that coefficient of X, so however many equivalents you're either losing or gaining. And of course, you have a positive change if the reaction is wherever the reaction is proceeding towards. So again, if you were given all products and then it was going backwards, then your products would be minus X and your reactants would be plus X. And then of course it's negative for whichever one is being consumed. And we'll solve for X. So we may need the quadratic formula, or we'll practice cases where we can kind of simplify to make the math easy for us. All right, so let's try our ICE table here. So let's practice this one, a little warm up. So now we have this reaction mixture. So dinitrogen tetraoxide gives us 2 equivalents of nitrogen dioxide. We're given our Kc is 0.36 at 100 degrees Celsius. And so it tells us that the reaction mixture initially contains 0.1 molarity of our nitrogen dioxide. So I'll give everyone a few minutes to kind of set that up, see if we can recall what to do based off of our last lecture. And then we'll go over it. And then, so let's at least check in real quick. So we have our initial concentration, so we don't have any reactants, and we have 0.1 molarity of products. And then what should I do for the change? So what's my change for my N2O4? Exactly. And so this is, it may look a little funny, but we started all with products. So that means, and even just looking at our equilibrium, so we can look, well, this is 0.36, right? It's not something crazy like 1 times 10 to the 34. That would suggest that it's all product, right? So this is instead telling us, well, we probably need to reform some of our reactants. And so yes, exactly. So it would be gaining X. And then, so this is gaining X. What is the change on our NO2?
Only 0.5 or 2x.
Yeah, so it would be minus 2x, exactly. Since you have, again, that coefficient, so you know you have to lose 2 equivalents of NO2 for every 1 equivalent of N2O4 you gain. So did we make it there at least in our setup? A little mixed bag, that's fine. That's why we're reviewing this. And then, so now equilibrium, this gives us, so 0 plus x is x, and then this is 0.1 minus 2x. And so now we can get ready to solve. And so what's just my K equilibrium expression without numbers, just with variables? So products over reactants, so that gives us NO2 squared, so don't forget to square it, over N2O4. And so now, at this point, we're ready to plug in, and it's all algebra from here. Oops, sorry. So we're given our equilibrium constant, so we can set this equal to that, so 0.36. And so first I'll just rewrite this before I plug in the numbers. And so that's going to be 0.1 minus 2x squared over x equals 0.36. And so now we just have to do algebra. Let's see, I guess we got a FOIL. Zero, one. Do we get this, or double check my math too?
You're missing the divide. Never mind.
I just want to make sure before I go crazy, because I think we're going to need the quadratic. So probably move everything over. Pull up my calculator. So then did we get this for what we need to plug into our quadratic? Just want to make sure I don't screw up this part. And then, who wants to remind us what the quadratic formula is?
-b plus or minus the square root of b squared minus 4ac, and all of it is divided by 2a.
Perfect. All right. And then we know, right, this is A, this is B, this is C. And so now we just need to do math. Oops, sorry. So then we should have two possible values for x. No, I wanted to do -1. Again, please double check my math. So I have those two values for x. Is that what people got? Okay, excellent. At least we're on the same page there. So now we have to go back and see, well, which value actually makes sense, though, with our equation. So we have, probably want to look at this one, because that's just plus x. So as long as x isn't negative, that doesn't matter. And so now we have 0.1 minus 2x, except, so which value of x doesn't work? Did you say the 0.17? Exactly. So right, we do 0.1 minus 2x. That's going to give us some negative number. So that doesn't work. I was just too lazy to plug it in. And so that means that this is our value for x. And so now to find our equilibrium concentrations, we just have to plug them in to our equilibrium. So that means our N2O4 is equal to x. Now we can say, so at equilibrium, our N2O4 is 0.01425 molarity. And then for our NO2, we have to plug it into this expression. So our 0.1 minus 2x and so I get 0.0715 for my equilibrium concentration of NO2. And then the nice thing about these types of problems is you can always plug it back in. So if you're not sure, you know, that was a lot of math where things could have gone wrong, you can always plug it back in to your original expression. So 0.0715 squared over, I already forgot our value for x, 0.014. So just a quick double check. And so that looks pretty good. So they had given us 0.36. We calculate back, you know, 0.36 essentially with sig figs. So that looks pretty good. So happy about that. Any questions on that one? watching the chat too, in case anyone's there. Yeah. So this all goes back to like trying to figure out what direction it's gonna go. And so if we look back at our initial concentrations, right, we had none of our reactants. And so we knew that it's gonna go to the left, so that's why we were adding our plus x. And then we know it's just 1x from our coefficients from our balanced equation. So that's a 1 coefficient. So we just gain 1x. So now let's try, we'll kind of try that problem again. So same problem, same temperature, so that means same temperature, Kc is the same, so it's still that 0.36. But this time the reaction mixture initially only contains the reactant and no NO. So see if you can at least do the setup, and then we can always go through the math together. So did we at least get this far for this problem? So I see some nods, so that's good. And so now, right, kind of opposite scenario. So now we have no products. And so now if we have no products, our Kc, right, is 0.36. So there has to be some products there. It's, again, not something extremely tiny that would suggest it wouldn't move forward. And so we know that it's going to be going in the direction to the right, again, to create more NO2. And so we set up our initial conditions from our problem. And then now this time, right, it's minus X as our reactant gets converted to product. And then again, don't forget that now we're going to be gaining 2X on NO2 since it has a coefficient of 2 there. So questions about this little portion here. So maybe we're feeling better. And so now equilibrium, we just have to write it. And so now we have to do some more fun math again. So I'll just rewrite, so our KC, and so this is all just kind of rewriting from before. So same equilibrium expression, now we just have different variables, so 2x squared then over 0.025 minus x is equal to 0.36. And so now at this point, right, just algebra again. So 4x squared is equal to, I'll distribute. And I'm assuming we're going to need the quadratic again. So move everything over. So do we get this expression? Excellent. So as long as you make it to here, so now at this point, it's quadratic formula time. Minus 4ac, so that's a plus sign there. And let's see, so at this point, I'm not going to do the subtraction because we have a negative minus an even larger number, so that doesn't help us. Can't have a negative value for x, but let's see, we do negative 0.36 plus 0.52306 and divide it by our 2a. So did we get 0.02 for x? Some nods, more nods. So 0.02. And so now that we have solved for x, our last little step is to plug it back in, and then of course I would do our double check as well. So 0.025 minus x to give us our final concentration of N2O4. So now at equilibrium, so that was 0.0046. And then that leaves 0.0203. And so it looks like our NO2 is about 0.04. And of course, we could always do our double check at the end. And so let's see, does this give us a good value? oops, sorry, I plugged the wrong number in. And so that looks pretty good again, so about 0.36. Questions? All right, so let's try a trickier one, where now it's not as obvious what direction it might be going at. So now we're given this reaction again. We've looked at it before. So iodine plus chlorine gives us 2 equivalents of iota chloride. And we're given the Kp. We're given all of them in pressures, so that's nice. We don't have to worry about anything like that. And so now we just, given our equilibrium, find the equilibrium partial pressures of iodine, chlorine, and iota chloride at these temperatures. So I'll give everyone a few minutes. So what do we have to do to figure out what our change is going to be? So which direction is it going to go? Yeah.
Because the Kp value is so high, I'm going to predict that it's going forward.
Well, let's check that because I can't tell just by looking at it. So let's see if your theory is correct. So let's just write our expression. So it's our concentration of ICl squared over our initial concentrations. And so now we can plug it in. I think you're correct just with this mental math here. And so all these values are 0.1. So if you do 0.1 squared over 0.1 times 0.1, so that's still 0.1 squared. So what do you get for K? Or I should have called this Q. That was my mistake. So let's call this Q. since this is just our snapshot. So what do we get for Q? So 1, and so yes, indeed, you're correct. So if our Q is at 1, right, we're not at equilibrium yet. So again, just think of that, okay, products over reactants. I should have a greater ratio of products. So now what are my change values here? So, yeah,
Minus X plus 2X.
excellent. So again, this was tricky. So once we establish with our Q what direction it's going in, now we can put in the change. And again, since it's going now in the forward direction, we're losing our initial reactant, so minus X. And then, of course, using your coefficient, it's gaining at a 2X rate. And so now at this point, it's your favorite part of math. So 0.1 minus X, 0.1 minus X, oops, and then 0.1 plus 2X. And so now we can just set up our algebra. And so this ends up being 0.1 minus X squared as well is equal to 0.36. Oh, that was my bad. I like that 0.36 value, I guess, a little too much. So 81.9. And so probably at this point, we want to take the square root of both sides. That's probably the easiest thing to do. And so I get 0.1 plus 2x over 0.1 minus x is equal to 9.04 roughly. And so now it's just more algebra. So I get x of like 0.0727. Is this what other people got? Just making sure. I could have always messed something up as well. Any confirmation or? Sorry? So we had to plug it in. So they gave us kind of like our starting point. And then so from there, right, we just plugged it into our equilibrium expression, which is the same thing as Q. That's why I kind of wrote them interchangeably. And then, so we just plugged in all these values. So you got 0.1 squared divided by 0.1 times 0.1. And so that just came out to 1. So, right, this was our Q. And so if we compare our Q to our KP, so this is QP, this is our snapshot. And since it's less, right, and we know it's products over reactants, if we need a greater ratio, we know we need to be forming more products.
So it's going forward because the Q is more and
Is less.
is less.
Yeah, because our KP is 81, right? And so, again, products over reactants. So if our KP is 81.9, then we know we need more products, essentially. And so that's how we knew which direction to go in with these X's here. So did other people get this value? I see some nods. And then if we weren't sure, or I was eventually going to plug it in to our expression then.
What did you get from?
Oops, what am I doing? There we go. So now we can calculate all our equilibrium values. So now at equilibrium, so we can solve, so our ICL is 0.2455. And this is ATM. And then our iodine and chlorine should be the same. Oops. So about 0.3 roughly. And so we can always plug it back into our expression and check. So I'm just rewriting our equilibrium expression. And so now we can plug those numbers in. And I'm only squaring this since they're the same. I'm not trying to confuse people. And so, yep, I got 81.22 out, which is pretty close to that 81.9. Question?
Units on that would be ATMs.
Yeah, so these now are all ATM concentration, since we're working with KP and pressure. Other questions on this one? Do some more math. And so sometimes we'll get into ugly looking equations. And so this means that we can use approximations to simplify the math. And so this is the 5% rule. And so when the equilibrium constant is very small, the position of the equilibrium favors the reactants. And so that means for relatively large initial concentrations of reactants, the reactant concentration will not change significantly when it reaches equilibrium. And so that means we can essentially assume that our initial concentration remains unchanged, so we don't have to do the minus x, and that, again, really helps simplify the math. And then the important part is that you need to check it. So once you make the assumption, you solve for x, and then you want to double check and make sure that your value of x is less than 5% of the initial concentration. So that's the only way the approximation is valid. If it's greater than that, then you have to do the whole math without any shortcuts and simplifications. And let me write that. So must check. So this should be part of your process. So AKA if you were given this on an exam and you made this assumption, you have to check it, or also probably knock off some points, because we have to check this assumption. All right, so let's see how this is going to play out. And so now we're looking at this decomposition of hydrogen disulfide. So 2 equivalents of H2S give us 2 equivalents of hydrogen and 1 equivalent of S2 gas here. And so this is kind of our first hint. So our Kc is 1.67 times 10 to the negative 7th, so that's pretty small. And so it's telling us, so our reaction vessel initially contains 0.025 moles of our H2S, and so find our equilibrium concentrations. And so they didn't give us molarity, but we could solve for it. And let's see, so we know it's going to go in the forward direction since we don't have any products. And so let's calculate our molarity real quick. 0.0125 over 0.5. So I get a molarity of 0.025, and they gave us a Kc, so that all is good so far. So now let's set up our reaction like before. And of course, we can also write out what our Kc would look like. So hydrogen squared times disulfide over our hydrogen disulfide squared. And we can do initial, so 0.025 molar, 0, 0. And then our change, so what's our change for our hydrogen disulfide? That sounded good. So minus 2x, oops, plus 2x plus x. And so now we're left with our equilibrium concentration. So 0.025 minus 2x, and 2x and x. And so now we can set this up just like we've been doing before. And so now I'm going to plug my variables into my equilibrium expression. So I have 2x squared over times x over 0.025 minus 2x equals Kc. And so now we're given something kind of nasty of like 4x cubed over 0.025 minus 2x equals Kc. And so now this is where it's appropriate to make our assumption. So again, small equilibrium constant. So this value shouldn't change too much. And so now we can just assume. So assume less than 5%. That goes away. And so now this just leaves us with 4x cubed over 0.025 is equal to Kc. And so that's 1.67 times 10 to the negative 7. And so now this is a lot easier to solve. And so now we just can finish. have to take the cube root. So I have an x of 0.001. First of all, is that what everybody got for x? Okay, I see some nods. So that looks good. And so now that we have our value of x, right, we have to double check this 5% approximation. So we have to take what our x is divided by our initial concentration. So that's just our 0.001 divided by our 0.025. And so make it a percentage. So it's just under there at about 4%. So yes, it was appropriate to make that. And so you'll want to just do like show some work for your check. So 0.001 divided by 0.025 equals 4%. So yes, it was appropriate. And so now we have our equilibrium concentrations. So H2, so at equilibrium, that means H2 is 0.002 for the concentration, and S2 is 0.001. And if we wanted, we can always double check too with our KC. So lots of ways to double check, double check. So then you have 0.002 squared times 0.001 divided by 0.025. And so let's see if that works. Oh, I should have squared this. It's like off by an order of magnitude. I don't like that. Not crazy that it's off by a lot, but it may just be that way. So a little fuzzy, but did we get other values for x?
I don't understand the 5% approximation. And I don't know if I might be the only one, and if I am, then we can talk about it or not. But I'm not sure how you got rid of the 2x. Is it just because the change is smaller than 5%?
Yes.
That's it.
Yes.
Is there any harm in just leaving that 2x in there and doing the math?
You would get a better answer, so probably when we're doing this double checking, if you left it in there. But I doubt many of you can solve a x to the third unless you just have your calculator do it, which that's not my expectation. You could, so again, you could do that. You can not make the approximation. But again, I wouldn't be able to do that on an exam as a student. But if you can, that's fine, and your answer would probably be better. So we're seeing the issue right with the approximation right here, is I'm not getting quite to what the KC is. But I kind of expected that since we did make an approximation there. I was just trying to see if I plugged in anything wrong. So Did that clarify your questions or no?
No, so 5% of what?
5% of your initial concentration.
Okay.
So that's why we found X, right? So we made our assumption. We solved for X, and I got this number. And then once you get your X, then you take 0.001 divided by your initial concentration to check, was that actually less than 5%? Yeah.
Were you saying that we make that assumption that we can do that because the KC is a very small number?
Yeah. So that's the other point, is this KC is times 10 to the negative 7. So that's not very much in the forward direction. So that's why, yeah, our change in X should be pretty small relative. So our double check doesn't work out as well, which is a little annoying, but that's what happens when you make these approximations. I'm just doing it again. So that's like a little off. But we did make an approximation. So can you just solve it with your calculator?
I mean, that's probably what I would try to do and then cry. So.
I don't know, is that because some people are better with the calculators, or you can like force Wolfram Alpha to do that, but that's why we make the approximation, because again, it's not my expectation that you can solve that x to the third expression. So yeah, so that being said, if your calculator, I don't even know what calculators do nowadays, but if it solves it for you without an approximation, like you can go ahead and do that. That's perfectly fine. But again, for me, I can't do that. I don't know how to do that. So I would just make the approximation and then just check your approximation. And then if it's not, then you would have to actually solve it. But again, I would need like a computer to do that. And that's not the expectation in this class.
Can you keep it like that, x to the 4x to the third? I'm going to try to see if my calculator can solve it.
All right, so you can, do you have this?
Yeah.
All right, yeah, so report back if what value the calculator gets, if we can get it. But let's talk about Le Chatelier's principle, especially because it'll be on your exam, hint, hint. Oh, yeah,
Can you scroll back up to your math? Oh, you did, okay.
and if anything is wrong with the math, just let me know. You got a different value for x.
So in your initial equation where you have the x cubed, or the 4x cubed, that 0.25 isn't squared?
Oh, that's probably why my math isn't working out well. I screwed that up. That was my mistake. So now you caught why my approximation is funky. Yes, I screwed that up. So I did not plug it in properly. I didn't read my own thing. So let's redo that. That makes sense. So let's erase all this. So that's probably why our double check isn't that close. So let's try that again. That will help us. So 0.025 squared times 1.76 times 10 to the negative 7 by 4 cube root.
So you keep the square, but you get rid of the 2x.
Yes, yes. And I apologize for dropping that. That was just my mistake. So then I get a different value for x. And now it's even tinier. So our approximation is even better. And so now plug this number in for our double check. Or our check and our double check. So 2.96 times 10 to the negative 4th over 0.025. So I know that works. And so now let's see if we do our double check, so we said H2 is 2x, now I gotta get rid of, so that means H2 is 5.9, 3 times 10 to the negative fourth, S2 was X, and we'll just assume that it's 0.025. So now if we redouble check that, that's why you don't want to skip any steps and you forget to square something. So now redouble checking. And I almost forgot to square this again. Oh, and that works out so much better now, doesn't it? I feel better. I knew something was not quite right. So thank you again for finding my mistake. And so now this makes more sense. It makes me feel better about things. So now we got 1.66 times 10 to the negative 7. So that's really good to our KC. And so this also makes us feel better about that approximation. All right, questions about that? Again, I apologize for the math error. All right, so let's talk about the last little bit here, Le Chatelier's principle. And so basically, right, this kind of tells us what direction things will go. It can also help us determine whether reaction is endothermic, exothermic, like you did in your lab. And so blah, blah, blah. Let's skip over this text for a second. And so let's go back and kind of look at these graphical representations, and then we can talk about all the word there. But basically what we're saying, so we have this reaction. Let's zoom in. And this is one of our classics, right? Just our dimerization or splitting. So N2O4 splits to NO2. And this goes back and forth to redimerize. And so if you're at equilibrium, so now we're just imagining, right? We're at equilibrium. We have some amount of NO2, some amount of N2O4. And then it kind of asks, well, how can we disturb the equilibrium? And so in this case, the equilibrium was disturbed by adding our product here. So more NO2 is added. And so this is just your artificial, like someone injected some NO2. But then which way will your reaction go if you add more product? Yeah.
Some of it will decay to become reactants.
Exactly, right? So it has to go back to equilibrium. So now we have too much product. And so we add product. It was at equilibrium. Now it's got to go back. And so we see that in this graph here. So we disturbed our equilibrium. So now some of that is going to be consumed. And then your equilibrium, right, is reestablished. And of course, your values are going to be different. So now you're going to have more N2O4 than you had before. You're going to have more NO2 than you did initially, but of course less than what was ever added and injected into there. And so now your equilibrium is reestablished. And so what about in this case? So now we're looking at our graph again. And so we're at equilibrium. And so now they disturb the equilibrium by adding N2O4. So now which way is the direction going to go? Yeah.
There's going to be more products as some of the reactants combine.
Yeah, exactly, right? So now we added more reactants. So now there's too much reactants, so that drives the formation of more product. And so we see that, right? We disturbed it. Now it's driving the formation of more product until equilibrium is kind of reestablished. Now what if we took away N2O4? So we're at equilibrium. We remove our reactants. So which way will the reaction shift? Left, right? So remove.
If you remove the N2O4, there's going to be less product, so that to shift it back to equilibrium, some of it will like compensate for the lack of NO2/4. Does that make sense?
Kind of, except so in this case, right, it's a reactant.
Right.
So we want to say that it's shifting left then to make more N2O4. So let me just write that out. So we were at this. And so now we remove our N2O4. So now we're removing reactants. So now we disturbed our equilibrium. And so to get back at equilibrium, it's going to shift to the left. So we can say right towards reactants again. And so we'd be consuming product. And so if we go back to all this text, so that's all that is saying. And so just kind of a recap. Remember, we're only looking at things in the equilibrium expression, so therefore it's not a solid, not a liquid. So we have like a big pile of carbon reacting with oxygen. It doesn't matter if we add or take away carbon, that's not going to change the rate. And so again, looking at these different scenarios, so if we were adding reactants, so we add reactants, then that's initially going to push it in the forward direction. So then we can say it's proceeding to the right until equilibrium is restored. Yeah. So yeah, so if we remove products, so now we can go back to this one. We'll go back to our scenario. And yeah, so you're just thinking, right, which way is it going to go? So in this case, if we remove product, so we remove NO2, so now we have less product. And so yes, that would shift it to the right. So it's going to have to make more product now to compensate. So shift right towards product. And so if you remember, that's where I brought up like that Dean-Stark reaction. So that's a way to drive a reaction forward. Again, you remove water, so you remove a product, and then that keeps that reaction moving forward. And so let's see, blah, blah, blah. So removing reactants. So now if you remove a reactant, so now it's going to go to the left until equilibrium is restored. And so again, if we remove products, then our rate of the reverse reaction will be initially increased until we're back at equilibrium. Let's see. Yeah, let's look at this for a second. So if we look at this reaction, so we have calcium carbonate, so solid, gives us, or decomposes to give us calcium oxide, which is a solid, plus CO2, so gas. So take a minute or two. So what happens if you add CO2 to the reaction mixture? Let's shift left, right, towards your products, towards your reactions. And then what happens if you add calcium carbonate? So what happens when we add CO to the mixture? Does it go left, right? Go for it, so someone else is volunteering.
It goes for the left.
So it goes to the left, exactly. So we added products, so now it's going to force it backwards. So left. And then adding calcium carbonate, so what happens? What did you say? Goes to the right. It's a big lump of solid though, yeah, so no effect. And so that's one of those ones you got to watch out for. So again, if you have water, that would be another reagent to watch out for. And so it doesn't matter how big your pile of calcium carbonate is, it's not going to.
Does it only work on gas?
So it only be for gases and then something with like a solution, so like molarity. But yeah, if we had had like, you know, H2O liquid reagent, I don't know, I don't have a good example. It gives us H2 plus O2, right? Adding water, you can't change the concentration of water for that one, so that wouldn't have an effect. Yeah.
How I think of it is that, especially with solids, when gases and aqueous solutions are reacting with solids, it's only reacting with the surface area, so there's not really anything you can do to change how, I don't know what I'm saying.
But yeah, that's
Yeah.
basically it, right? So it's just dependent on the surface area reaction, so it doesn't matter how big that pile is, it doesn't change like the concentration. And then, oh, I lost my mouse here. So blah, blah, blah. So some things that we should talk about. So what happens if we change our volume at equilibrium? And so, of course, this would be for gases. And so, of course, if you decrease the volume of a container, that increases the concentration of all the gases. And so it increases our partial pressures. Obviously, this doesn't have any effect on solutions, so this is only for gas reactions. And so again, according to Le Chatelet's principle, the equilibrium should shift to remove that pressure. And so the way the system reduces the pressure is to reduce the number of gas molecules in the container. So that means if your volume decreases, your equilibrium shifts to the side with fewer gas molecules. And so let's look at this little example here. So this is our good old Haber-Bosch process once again. And so the reason why this reaction, it takes place at high temperatures and high pressures, and you can kind of see why. So they have to force this reaction. And so if you look at the molar equivalents, you have 1 mole of nitrogen plus 3 moles of hydrogen. So that's 4 moles total of gas versus your 2 equivalents of ammonia. So that means if you decrease your volume, right, or increase your pressure, that's going to cause it to shift to the right then, so that's the side, again, with fewer gas molecules. And so, of course, conversely, if you decrease the pressure, so if it's at equilibrium, now you decrease the pressure, it would shift to the left then to go ahead and make more moles of gas and compensate for that reduction in pressure. And so again, to get this Haber-Bosch process going, it's high temperatures, high pressure, so you can keep making that ammonia. It's a very energy-intensive process, but kind of seeing why. And crap, we took a lot longer in this chapter than I expected. So before I let y'all go, we should at least mention this, because again, it will come up, hint, hint. And so when we're talking about the effect of temperature, or you're looking at your lab and you're trying to figure out, well, was that reaction endothermic or exothermic? So we can treat heat as kind of a product or a reagent. And so for our exothermic reaction, heat is our product. So if we have an exothermic reaction, right, if you add heat then to this, which way would it shift? Yeah.
It's going to go to your reactants.
Exactly. So add heat. So now it's going to shift away from the products, because if you're producing heat but then heating it up, right, it's not going to want to make more heat. So now it's going to shift to the left to favor your reactants. And so conversely, let's skip down. So that means for an endothermic reaction then, so now heat is like a reactant. And so if you add heat to an endothermic reaction, which way will it go? So it'll shift right, and that tends to make a little more sense because, okay, endothermic, we know it has to add heat, so yeah, obviously that's going to make it go to the right and make more products. So then with the lab, you can ask yourself, okay, we heated it, and then which way did it go? Did it make more products? Did it get darker? Or did it go lighter? Suggesting, again, whether it's endo or exothermic. So I won't spoil it all. And yeah, I think we're over time, unfortunately. All right, I guess we have to end there for the sake of time, and hopefully on Thursday we can get through chapter 20. So a quick preview of chapter 20 is just acids and bases. So not too much math, but prepping us to do more math with acids and bases in spring quarter. So hopefully we can get through a chunk of that. All right, thank you guys. Sorry for going over time, and I will see the Tuesday lab people at the very least. So we have to do our equilibrium lab. Oh yeah, and if you want to hang on to your labs till after lab, that's fine. And then I have people's ungraded labs, so I can hand those back in lab, or I'll try to grade them maybe. But all right, thanks again.